Hello everybody. We looked at how to find the pressure at a different depth from a cylindrical vessel in part 1 video. Let's solve question number 2 by using continuity and Bernoulli's principles and equations. Looking at the question in detail, water flows in the horizontally oriented pipe that has an inner diameter of 15 centimeter and narrowed down to 10 centimeter, as you can see from the circular cross-section of the pipe. When the broad region has static pressure of 87 kilopascal with the velocity of 3.50 meter per second, what is the static pressure in the narrow region in kilopascal? For convenience sake, we can say the broad side as region 1 and narrow side as region 2. And then the water density rho is given as 1 gram per centimeter cube. For incompressive fluid, the volume flow rate stays constant, which means the amount of water flows in at region 1 must be the same as the amount of water flows out. That means Q in at region 1 is equals to Q out at region 2. And to calculate the speed of the fluid at position 2, we can use a continuity equation, which is rho 1 A1 V1 is equals to rho 2 A2 V2. In this question, the fluid running through the pipe is water, which is homogeneous solution. We can cancel the rho 1 and rho 2 here because they are the same fluid with the same density. And we can rearrange the formula to get V2, which would be V2 equals to A1 over A2 times V1. To calculate the cross-sectional area of the pipe, we can use the formula area that is equals to pi r squared, which is totally fine to use, but as the radius is half of diameter, we can change this area formula into pi, that is half of diameter square, that is pi over 4 d squared. So we can substitute into the V2 here. That become pi over 4 d1 over pi over 4 d2. Let's put the parenthesis. Times V1, which is given as V1, which I'll just write here. And we can cancel pi over 4 here. So that is d1 over d2 times v2. And we don't really have to change the diameter into meter, as we are just squaring the ratio between the diameter. And after we plug it in, 15 centimeter over 10 centimeter times 3.5 meter per second, that is equals to 7.875 meter per second. Bernoulli's principle is the reduction in pressure which occurs when the fluid velocity increases. And let's apply the concept to the question. The fluid at position 1 has higher area than the area 2, which leads water to flow slower at position 1 than P2, thus the P1 will have higher pressure than the P2. Let me summarize what I just explained. Area at 1 is bigger than area at 2, which leaves velocity at 1 would be lower than velocity at position 2, and that gives higher pressure at position 1 than the position 2 here. Now let's use Bernoulli's equations to find the pressure at position 2. P1 plus 1/2 rho V1 squared plus rho GH1 is equals to P2 plus 1/2 rho V2 squared plus rho GH2. As the center of the two circular cross-sections are on the same reference line, which is in the dotted line in the diagram, this means they are at the same height. So there is no difference in H1 and H2. In fact, you can cancel these two. So to find the P2, that is equals to P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared. That is equals to P1 plus half rho V1 squared minus V2 squared in parentheses. And we can plug it in those calculated value with SI units to get to the final answer. That 87 kilopascal is 87,000 pascal plus 1/2 rho, that is 1 gram per centimeter cube. But from previous lecture video, we found that 1 gram per centimeter cube was same as 1,000 kilogram per meter cube. And V1 is 3.5 meter per second square, and we subtract 7.875 square meter per second square. This will give you the answer of 62,117.18 Pascal, which you can write it as 62.1 kilopascal. The key note to remember is that to find the final pressure in kilopascal, in fact, we didn't have to do any unit conversions from the first place. Just like we reviewed from the previous hydrostatic pressure calculation, in part 1, the density unit gram per centimeter cube and pressure kilopascal unit can cancel nicely, and even without doing any unit conversion, you can still get the same static pressure of 62.1 kilopascal as I calculated on the left. Thank you very much for watching the video, and have a nice day.